We present SoFar, language-grounded orientation bridges, spatial reasoning, and object manipulation. Let's begin by showcasing our long-horizon demo, making breakfast. First, upright the coffee cup and place it to the right of the plate. We need to understand the up direction of the cup and align it with the z-axis direction of the world coordinate system. Second, put the bread into the plate. This is a position-related pick-and-place task, and we need to accurately identify and locate it. Then, put the broccoli into the spoon. This is also a position understanding task, and the generated motion trajectory needs to consider environmental collisions. Finally, grasp the handle of the knife and cut the bread. We need to understand the cutting direction of the knife and point it towards the bread. Next, we will introduce our motivation and methods. We propose that the interaction between objects involves not only position but also orientation relationships, such as the direction in which a door opens, the direction a car moves forward, or the orientation of a cup's handle. These relationships jointly determine the pose of objects and the robot end effector. In this paper, we introduce the concept of semantic orientation, which defines object orientations using natural language in a reference frame-free manner. To support this, we construct OrionText 300K, a large-scale dataset of 3D models annotated with semantic orientations that link geometric understanding to functional semantics. We import 800,000 3D assets from Objaverse into Blender. After careful standardization and lighting, we rendered 6 standard views. Then we use ChatGPT to filter the objects, removing noise, meaningless, scene, oblique, and low-quality data. Finally, we generate semantic orientation pairs on the standard view, a free text that may involve interactions between direction, part, and action. By integrating semantic orientation into a VLM system, we can generate robot actions with 6 DoF constraints, using a RGBD camera and a language instruction as input. We first use a VLM to parse instructions involving objects and directions, such as camera and drill. Then, we use visual foundation models to segment objects and obtain 3D point clouds. Finally, we use the orientation model to generate the interactive orientation of objects and form a JSON format 6 DoF scene graph. The scene graph will be input to a VLM to generate task planning and robot action. Extensive experiments in simulation and real-world demonstrate that our approach significantly enhances robotic manipulation capabilities. For example, 60 tasks and more than 100 assets in real-world experiments, and 74.9% accuracy on simpler environment. With its powerful spatial reasoning ability, SoFar can perform complex spatial logical manipulations, such as place the right bottle into the box and arrange it in a 3x3 pattern. This ability is crucial in factories and retail and does not require any training or data. Next, we will show more long-horizon demos, including tidying up the table objects into drawers and neatly arranging water bottles on shelf, etc. Our model can complete tasks on randomly scattered items, as well as articulated object manipulation. SoFar has strong generalization abilities, which can generalize across multiple objects, scenes, camera views, and even various embodiments. SoFar can be deployed on dexterous hands in soccer and can also support input from cameras with different views. In addition to manipulation tasks, our semantic orientation can also be used for robotic navigation. For tasks involving object orientation, we can generate semantic orientations to guide the generation of navigation trajectories, such as the front direction of a microwave oven and the back direction of a chair.